MVUE. At times they could have uniform minimal variance unbiased estimator. Okay, so once again, I'm welcoming you to this topic. There are Blackwell theorem and minimal variance unbiased estimation. In the outline today, we got a lot to do today. In the outline, I'm going to have a recap on sufficiency that we've done before. Then I'm also going to have a recap on Fisher-Neyman factorization theorem. Then I'm going to introduce you to Lemma-Skeffey theorem because both Fisher-Neyman factorization theorem and the Lemma-Skeffey theorem can help us to figure out a sufficient statistic. So the one we've done before, we actually made use of Fisher-Neyman theorem. So you're going to see today how Lemma-Skeffey theorem is also going to work. And of course, after that, we're going to go into minimal variance unbiased estimation. Let me first tell you this. What is the connection between all of these? The Rao-Blackwell theorem actually make use of the idea of Fisher-Neyman factorization, for us to be able to derive minimum variance unbiased estimator. That is just the story. Okay, and that is why I'm actually bringing Fisher-Neyman factorization theorem again. But let me first, let me review sufficiency before I go into Lemma-Skeffey theorem. Of course, we got so many properties of an estimator. The whole idea started from the situation where we're trying to figure out the value of unknown population parameter. And of course, because we actually are going to be using sample information, we need a particular estimator, which we call method formula, that we can use on data. And of course, if we really want to trust our estimator, we expect our estimator to possess some properties like unbiasedness, efficiency, consistency, sufficiency. And if you look at the sufficiency, we believe that if we are able to derive a sufficient statistic, we believe that we actually found a compressed way of actually figuring out the true value of parameter. And of course, we said that if we can actually derive the probability distribution of the raw measurement, if given the sufficient statistic can be we can have, if it is independent of theta, then we say that the statistic is said to be sufficient. And by Fisher-Neyman factorization, they provided us an idea that, okay, if you know the probability distribution, all what we can do is to get the likelihood of that probability distribution. If we can actually split the likelihood of the probability distribution into two functions in such a way that one contain the parameter and the other one does not have the parameter, then we have already secured what I call sufficient statistic. So the Fisher-Neyman factorization theorem actually use the idea of splitting the likelihood function into two functions in such a way that one will have the parameter in it and the other one is going to be independent of that. What is new? Okay, what is new is Lemma-Skeffey also have their own approach. Okay, Lemma-Skeffey has their own approach, but let me tell you this: the Lemma-Skeffey actually use the technique of likelihood ratio. Okay, use the technique of likelihood ratio. And if at the end of the day, okay, the ratio of the likelihood actually give us an expression that will be independent of theta, okay, they can also conclude on sufficient statistic. Okay, so whether we're using Lemma-Skeffey theorem or Fisher-Neyman factorization theorem, all what they are actually looking for is sufficient statistic. Okay, the only thing is that they're going to do that in a different way. Okay, the Neyman factorization theorem is using the idea of factorizing or splitting the likelihood of the distribution into two functions. But for the Lemma-Skeffey, it's actually going to use the idea of a likelihood ratio test, which means the two of them use likelihood. Neyman-Fisher, splits the likelihood into two functions, but the Lemma-Skeffey is actually going to have two forms of likelihood, and we're going to find the ratio. So let's take a look at an example here. This is an example. If you take a look at this guy now, okay, if you take a look at this guy now, okay, that is the likelihood, it's talking about the likelihood ratio. Give me 1 second. Let me see if I can use my pen here. Okay, so if you take a look at that guy now, okay, the numerator is likelihood, the denominator is still likelihood, but except that we're just using X and Y, we believe that, the Lemma and Skeffey believe that, okay, let's say we got, we're going to construct two likelihood. The only thing we're going to change the random variable. First, there's a likelihood for random variable y1 to yn, okay? And we're going to have likelihood for random variable x1 to xn, okay? Now, when we find the ratio of the likelihood, okay, we're actually going to identify condition under which the ratio of the likelihood can be independent of theta. Okay, so because of that, I actually want us to solve the example in the textbook, 9.66 in the textbook, and that very example actually talk about, giving you this, the likelihood function takes on different value depending on blah, blah, blah. And it said a method for deriving a minimal sufficient statistic developed by Lemma and Skeffey use the ratio of the likelihood, just like what I said. Now, and after all that, he said we should show that using the Bernoulli now, okay, using Bernoulli distribution, like I said, they're going to give you the probability distribution. Now, this question in the textbook is now asking you to use the knowledge of, Lemma, Skeffey, to be able to show that the ratio of the likelihood of a Bernoulli distribution is actually going to be given like this. And, if the ratio is like that, okay, and the parameter in Bernoulli is P, under what condition do we expect that expression to be independent of theta? That will only occur if that exponent equal to 0. Do you see the exponent? I'm talking about this guy here. If that exponent equal to 0 will mean this guy here, right? If that exponent equal to 0 will mean summation x equal to summation y. Okay, now this is what we're actually going to do. Okay, I'm going to walk you through that now. Okay, let's say I first want to show this. I first want to show this because they're going to give you Bernoulli. Okay, now I'm going to show this guy now. Okay, now if I'm working with Bernoulli random variable, let's say f of x, yesterday on Wednesday I said whether discrete or continuous, at times you can use f, that's no problem. Okay, so Bernoulli has P, okay, raised to power X, right? And 1 minus P, right? Raised to power 1 minus X. Okay, what is the set space of Bernoulli? Is 0 to 1. This is Bernoulli, right? Now, if f of s equal to this, okay, because I want to use the idea of Skeffy lemma, okay, I'm also going to say f of y. Do you see that? I'm also going to have f of y, okay, which is going to be p raised to power y, okay, then 1 minus p, okay, raised to power 1 minus y, okay, you see that? Okay, I want to use the idea of Skeffy, lemma Skeffy, okay, factor, so the next thing I'm going to do is to find the likelihood, because, Skeffy, lemma Skeffy is actually talking about the ratio of the likelihood, okay, but the one in the numerator has to be the one that has to do with x. The denominator has to be the one that has to do with y. Now, when you take a look at this now, I want to get the likelihood. So the likelihood of x, okay, don't forget, when I put a bar, when I put that, I'm talking about x1, that's another way to write x1, x2 up to xn, okay? Or given p, given the parameter now, the likelihood, okay, is actually, I want to write the likelihood of that joint PMF. So I can rewrite that as p raised to power sum of x, okay? Then 1 minus p, okay? What is 1 in n time? It's going to be n, right? That will be n minus summation x. Okay, this is the likelihood of Bernoulli distribution. Now I'm going to write the one that has to do with the y now. Don't forget, what do we want to do? We actually want to use the idea of, lemma Skeffy. I'm still going to write the same thing, except that, so where I have x, I'm just going to have y. So p, okay, summation y, okay, then 1 minus p, okay, raised to power n minus summation y. Okay, now if you take a look at here, we want to do the likelihood of the x divided by likelihood of y. Okay, so in order not to waste my time, I can just say this divided by this divided by that. You see that? Now, if I say this divided by that, oh my God, the idea of algebra will be in use now. Okay, when you take a look at p here, you got a p here, right? You get another p here, right? Okay, if I can just write p, okay, then I can write summation x, right, minus summation y. Any question? Okay, I can write summation x minus some, but if I don't want to do that, I can actually do this. Give me 1 second. If I don't want to do that, I can actually simplify first. Okay, I can say 1 minus p. If you take a look at 1 minus p in the denominator, 1 minus p in the numerator, I can split that into one. I'm seeing something that will cancel out. 1 minus p raised to power n. Cancel out. Okay, I'm actually going to have this p raised to power summation x, and here I'm going to have 1 minus p, okay, raised to power negative summation x, okay, divided by p raised to power summation y, okay, then 1 minus p, okay, raised to power negative summation y. Okay, take a look at that. Now, if I want to combine, there's something I want you to see. If you look at the numerator, if I want p and 1 minus p to carry summation to be raised to power summation x, then it means 1 minus p, we're going to go to the denominator, which means I'm actually going to have p. So if I want to rewrite, I'm going to write p divided by 1 minus p, right? And that is going to be raised to power summation x. This is going to be for the numerator. If I'm going to do the same for denominator. When I do the same for denominator, okay, in the denominator, I'm still going to have p divided by 1 minus p raised to power summation y. What am I going to do? I can just take, if this and this are the same, when that one goes up, they're going to be summation x minus summation. It's going to be this guy here. It's going to be this guy here. That is why algebra is very, very important. Algebra. Now, when that guy is that guy, if I want p to disappear, what is p? Parameter, right? Then that is when that exponent equal to, if summation x equal to summation y. What happened? Then it should be independent of p. And that is how the Lemma-Skeffey theorem work. Any question? Go ahead. Oh, we don't it's not as if we prefer. What is common in literature is Fisher-Neyman factorization. But I'm just trying to say this is an alternative. What is what? Oh, that is why, you said, why, what if this take longer, right? And that is why in life, when there's a problem, we got more than one approach. There are some approach that waste time. There are some. So we are going to be the one as individual that will figure out the one that will work very fast. I love that. But what if examiner put it to you? Use Lemma-Skeffey. Does that make sense? Okay. Now, and I think I gave another example. This is from a given distribution. That distribution is Weibull. I take the distribution. Let me see. I think it's around that I'm still gonna let me see. Yeah, here. Here. That distribution. So whatever distribution you are giving, just know how to get the likelihood by Skeffey ratio of the likelihood has to be independent of theta. Like if you take a look at let me show you. If you take a look at what it asks here now, okay, if you take a look at what it asks here now, okay, after they derive, this was what they derive. What is the condition under which that would be independent of theta? When summation s squared equals summation y squared. So therefore, summation y squared is a sufficient statistic here. The one we did the other time, the sufficient statistic was summation s. Why do I say summation y squared? Why not summation s squared? Because, please take notes. Why do I say summation y squared? Why not summation s squared? Because I say summation y squared because the distribution initially was given in terms of y. I'm going to show you now. Do you see the distribution? Was given in terms of y. Do you see here? I'm talking about this guy. This is the distribution I talk about. What do you see? The random variable is y. Okay, then I'm going to say summation y squared. Does that make sense? Okay, now I think I've walked you through you know that, and I want to go into today's topic. Now you know how to figure out sufficient statistic. If you know before you come to Rao-Blackwell theorem, I'm going to say that again. Before you come to Rao-Blackwell theorem, you need to first understand how to figure out sufficient statistic. You need to first understand Fisher-Neyman factorization, either Fisher-Neyman factorization theorem or Lemma-Skeffey. Now let's come to Rao-Blackwell theorem now. What do we intend to do? What do we intend to achieve with Rao-Blackwell theorem? The Rao and Blackwell, you know, what they did is just to figure how to use the knowledge of Fisher-Neyman factorization technique, okay, of determining sufficiency to be able to come out with an estimator that will have a minimal variance and at the same time unbiased. Okay, that was why I said sufficient statistics, I told you, play a very important role in figuring out good estimator, okay, for the parameter. You know, we always want a good estimator for the parameter. Now, take a look at it. According to Rao-Blackwell now, if theta cap is an unbiased estimator for theta, you know, you already have your theta cap and your estimator. You now say if U is statistic that is sufficient, you know, the other time I was using T, it doesn't matter. Yeah, I'm saying a sufficient statistic. I use T, the other time I'm using U now. Okay, if U is a statistic that is sufficient for theta, how will you know that? Either by Fisher-Neyman factorization or by Lemma-Skeffey theorem. Then there is a function of U. There is a function of U. What is U? U is a sufficient statistic. There is a function of U that is also unbiased for theta, okay? And the variance of that function, it will be less or equal to the variance of the estimator, which means that variance is even better than the variance of the estimator, or they are equally efficient. Okay, if we seek an unbiased estimator with small variances, we can restrict our search to estimated our function of sufficient statistics, which means if we actually looking for an estimator with a small variance, then we have to make use of sufficient statistics. And if we want to make use of sufficient statistics, how are we going to get sufficient statistics? We're actually going to go by way of Fisher-Neyman theorem or by Lemma-Skeffey theorem. Okay, now this is Rao-Blackwell. Let me show you the mathematical. Please, I need you to pay attention now to this. Let theta cap be an unbiased estimator for theta. Your theta cap is an estimator now, such that the variance of that theta cap exists, is determinate. Okay. Now, if there exists a sufficient statistic U that you've derived, probably through Neyman or through Fisher-Neyman factorization or whatever. Okay, now we want to define a function of that U, a function. You remember in SAT 4101, when you have a random variable, we can also talk about the function of a random variable can also be a random variable. Now the theta cap star now, the theta cap star is a function of the sufficient statistic, and that very function has an estimator in it, also asks what the sufficient statistic, and that was why we say expected value of theta cap given you. Now, if we're able to show that this is unbiased, is to show the expectation of the expectation, which is going to be theta, and we realize that the variance of that function of sufficient statistic is less or equal to the variance of the estimator. Okay, this is Rao-Blackwell theorem. Now, you know what if this happened, the Rao-Blackwell is going to say, okay, you know what, you've been able to derive, using the idea of your sufficient statistic now, you've been able to derive an estimator that is unbiased and has a minimum variance. That is where we can conclude that. And because of that, we're going to make use, we want to first show that the expectation of the linear combination, don't forget, theta cap equal to what, theta cap star equal to what you have in the parentheses. We want to show the world that theta cap star is unbiased. Theta cap star is a function of what? Sufficient statistic. A function of sufficient statistic is also a random variable. Okay, and that function of sufficient statistic is the expected value of theta cap given u. U here is sufficient statistic. When I take the expectation of that is because what you have in the parentheses is theta cap, and the expected value of theta cap is equal to theta. Therefore, we've been able to show that theta cap is unbiased. Not only that, theta cap is unbiased estimate for parameter theta. Not only that, the linear function, the function of sufficient statistic is also unbiased. Now, if you now want to talk about the variance, okay, now if you go back to what you've done in 4101, for instance, the variance, give me 1 second, I'm gonna I'm gonna look for a space. Let me see if I can find, I think I created, okay, here. I'm gonna look for a space here. Now from what you've done in 4101, if I have a random variable y1 and y2, right now, the function of sufficient statistic is looking like a conditional function where we're going to say expected value of theta cap giving u. Okay, now that will remind us in statistics when I have y1 and y2 that are random variable, and there is possibility y1, okay, we have a conditional probability y1 given y2. Okay, now the variance of y1, this is from the theorem, this is from 4101 you did before. The variance of y1 is going to be equal to the variance of the expectation, the variance of expectation of y1, okay, given y2, given y2, give me 1 second, let me erase that. I think I want to write y2, okay. Okay, given y2, okay, plus, okay, plus, okay, the expectation, okay, of the variance, of the conditional variance of y1 given y2. This is from statistical theory. Now, when you take a look at what I'm trying to show you now, this is from statistical theory. We have a y1, we have a y2, and y1 given y2, the variance of y1 is going to be equal to the variance of the conditional mean of y1 given y2 plus the expectation of the conditional variance of y1 given y2. You know what we're going to do now? Our y1 here is going to serve as the estimate of theta cap. Our y2 is going to be a function of sufficient statistic. Now, Rao-Blackwell used this approach, and you're going to see something now. You're going to see something now. That was how he was able to, give me 1 second. Okay, so that was how he was able to write this. You see that? The theta cap here is like y1 equal to the variance of the expectation, okay, of theta cap given u. U here is the sufficient statistic. So u here is acting like a y2. Theta cap is acting like a y1. So the variance of theta cap equal to that. That's from statistical theory. And let me tell you this. You know, this guy here, that would be the variance of a theta cap star. What is theta cap star? Theta cap star is actually a function of what? Sufficient statistic. Okay, that was why we see that. And this guy here is still what we have here. And you know what? Because I'm talking about expectation of a variance, if you take a look at this guy, I'm talking about expectation of a variance, and I expect variance to be what? Positive. That would be greater than or equal to 0. Because of that, you can now see that this guy here is either is going to be equal to the variance of estimator if this guy equal to 0, or if that guy is greater than 0, then the variance, okay, of the estimator will be greater than the variance of a function of a sufficient statistic. And that is what we want. We want a situation whereby the variance of a function of sufficient statistic will be less than the variance of the estimator. Therefore, by Rao-Blackwell theorem, they can now conclude that your estimator is unbiased and also has a minimum variance in the class of unbiased estimators. Any question? Okay, now we want to go through an example. Let's go through an example. This is where the question is going to come. You're giving a, take a look at this. If you take a look at this question now, okay, you're told that you're working with Bernoulli. The very first thing they ask you to do, use the factorization criteria to find, because if they ask you to find minimum variance unbiased estimator for the parameter, you need to first use Fisher-Neyman factorization theorem. Does that make sense? Okay. Fisher-Neyman factorization theorem is more popular than Neyman-Skeffey. Does that make sense? The Neyman-Skeffey is using the ratio of likelihood. That is not popular, but this guy is popular. Now, what are we doing here? We get the likelihood, and we factorize. What happened? We got two functions, right? Okay, one depends on the parameter, then the other one does not depend on the parameter. This is using a Fisher-Neyman factorization theorem, and based on this, we realize that summation y is a sufficient statistic. Any question? Now, if summation y is sufficient statistic, what they ask us to do is actually, give me 1 second. What they ask you to do is to give, anytime you see that, it means minimal variance unbiased estimator, and the only way to do that is to first derive sufficient statistic. You can derive sufficient statistic either with Neyman-Skeffey or with Fisher-Neyman factorization, but in this question, it said use factorization theorem, a criterion, and the factorization criterion belongs to who? Belongs to Fisher-Neyman. Okay, after that, now, if you take a look at this guy now, what do you think will be the function if summation y, we say summation y is sufficient statistics? Okay, can we define a function that we have a sufficient statistic? Of course, what is pickup? What is the estimator? Oh, estimator is the same thing as summation y divided by what? Divided by n. You remember? This guy here, the whole of this guy now, summation y divided by n. In this summation y divided by n, that is a function of sufficient statistic, because here now, the sufficient statistic is part of this estimator. Now, but P cap, we've derived that before. If P cap equal to y bar, what is the expectation of y bar? It's mu, it's unbiased. Not only that it's unbiased, what would be the variance? We've proved in this class. The variance of P cap, okay, when n is sufficiently large, of course, it's actually going to be small. That's all about that one. Now, let me go to more rigorous problem. Okay, so that is what I'm explaining here. Okay, you know, my U now, if this is my U, is sufficient that we just derive. Then this guy here, what is U over n? Don't forget, U is summation y, right? Summation y divided by n is P cap. What is the expected value of P cap? It's P, because we proved that before. P cap is unbiased estimator. And don't forget, U over n is y bar. And y bar is an unbiased estimator for P. Therefore, we're actually going to say y bar, you know, P cap equal to that is minimum variance unbiased estimate. I want to go into more rigorous. I want to go into continuous probability distribution. You are given this. And look at the question. The question just asked directly. Look at the question. You see the question? Given that, you're going to do a lot. 4 of us, you need to 4 of us get your sufficient statistic by way of Fisher-Neyman factorization theorem. That's what we're doing here. What are we doing here? Looking at the distribution, getting the joint PDF. I told you, practice how to get. I remember when I was in college, when I was doing this, I obtained the likelihood function of all existing distribution in statistics. That was what I did. All existing distribution. You can go online, you're going to see the list of probability distribution. And what I did during my time, I get a likelihood function for all of them. So the likelihood function for this is like the joint, right? And in the end, this is what you actually what you're going to get. Say, take a look at this. 2 is a constant, right? That would be 2 raised to the power n. Theta is a constant. That would be theta raised to the power n. But y, that's a product. Y1 times y2, blah, blah. That's why you see y1 up to yn. And where exponential is power negative y squared over theta, then so that y, we're going to have a summation. Or you have a joint. Now, take a look at this guy now. I splitted that into 2. A part as parameter theta, and the other one does not. Now, therefore, we've been able to use factorization theorem now. And if you focus on the one that contains parameter theta, then your focus should be on something that has to do with the variable. Therefore, if you take a look at that, summation y squared now is a sufficient statistic. Okay? By Fisher-Neyman factorization theorem. Now, after getting sufficient statistic, you know, let me tell you this. When we're working with a proportion binomial the other time, it was easy, you know, obtaining minimum variance unbiased estimator. But right now, we're working with continuous, okay? And here, you know, we said the sufficient statistic summation y squared, okay? Now, we need to be able to consider if this is a sufficient statistic, then the function of sufficient statistic we're going to consider is going to be a y squared. You know, we have a summation y squared, right? We got a summation y squared, right? Okay, the other time for Bernoulli, it was summation y. And we quickly remember when we have summation y, okay, the function of that statistic that we can actually use should be summation y over n, and summation y over n was a p cap, and because of the theorem that we know, expected value of p cap is p, of course the variance of that will be minimal. But for this, we're actually going to consider y squared. If I have a y squared, then you need to go by method of Jacobian transformation that you've done in start 4101. If W follow, this is what I'm going to do now. If Y follow what does Y follow? Y follow Weibull. This distribution is Weibull. Then I need to be able to know, okay, Y square will follow what? Where do I get Y square? Y square is part of Y square is here. Do you see here? Y square is part of the sufficient statistic that we derive using Fisher-Neyman factorization theorem, summation y squared. But right now, we need to be able to investigate what is the distribution, because if I want to talk about expected value of y squared, I need the distribution of y squared. Now, and I'm going to define a new variable called w equal to y squared. Then if w equal to y squared, then what is my y? Y will be equal to square root of w, right? Now, if you revise what you've done in start 4101, if you need, maybe you want to have a kind of recap on that, you can visit with me during my office hour. What am I doing here? This is a method that I'm going to use. If I want to get the f of w is equal to y squared, using what we call this a Jacobian transformation, what I'm going to do, I'm going to plug in square root of w in place of y in the function. Then I'm going to perform a derivative of that. After doing that, this is what I got. Now, this is a distribution for W. What does W stand for? W stands for y squared. That's a probability distribution for y squared. If I know the probability distribution for y squared for a particular variable, I can figure out the expectation. What am I doing here? I want to find the expectation. And if you take a look at this, what we have is a well-known probability distribution. That's an exponential distribution. An exponential distribution, I don't even need to conduct a rigorous statistics here, because when our exponential distribution has a mean of theta, the variance of theta squared, okay, I can just, that was why I actually have this. What happened? Expectation of a function of a sufficient statistic is unbiased, because the expected value of that gives us theta. One of the conditions of Rao-Blackwell theorem satisfied. Now, if that happened, if I now want to go back to my sufficiency, what was my sufficiency here? Summation y squared, right? Okay, it's just going to be expected value of that. Instead of, I'm just going to say n theta, because summation is n theta. And if I have that, what will now be my my estimator now? That will be on as a minimum is going to be this. What do you see now? Sufficient statistic is part of this estimator. So what is sufficient statistic? Summation y squared, right? Okay, what is the estimator? 1 over n summation y squared. Any question? And that was why we said this is an unbiased estimator for theta. That is a function of the sufficient statistic, that therefore theta cap is a minimum variance unbiased estimator of Weibull parameter theta. I think I gave this another example. You give a normal distribution with unknown mean, okay, unknown mu and sigma squared, okay. We don't know. We don't, we got 2 parameters here. The reason why the other time that I wrote theta cap, I wrote this. When I wrote that, then the sufficient statistic is also going to be a vector. Does that make sense? Now, right now, we don't know mu, we don't know sigma squared. We can go by way of factorization again. Fisher-Neyman factorization. Now, when you take a look at the Fisher-Neyman factorization, okay, now this is what we call a jointly sufficient statistic, because we have more than 2 sufficient statistics, because of the fact that we actually want to figure out 2 parameters. Now, what are we going to say here? Summation y squared. When you take a look at summation y and summation y, they are sufficient for the mu and sigma square. And don't forget, the function of this sufficient statistic summation y will be summation y over n, which is going to be y bar. Naturally speaking, expected value of y bar is going to be unbiased. The variance of y bar is going to be minimal. We all know that. Not only that, what about summation y squared? Okay, summation y squared part of the function of the surveillance analysis, we also have overhang, which has something that has to do with the sample variance. And in this class, we've already proved how efficient is the sample variance, how consistent, and of course, when an estimator is efficient, what is the meaning of efficiency? That's a minimum variance. That's all we mean. Okay. So that is how we derive that. Okay. Now, lastly, this. You are given this distribution exponential. Okay. And they say find an minimum variance unbiased estimator for that, for the variance of that. Okay. So take a look at that. You know from the distribution. Okay. What is the expected value of y? That's going to be theta. That's an exponential. The variance is theta squared. Okay. We know that from that. Take a look at that. Okay. Now here, MAU of the variance. Okay, of the variance. That's what we mean. Now, if I want to do the MAU of the variance, I have to use the fact that, take a look at this. What is the expected value of the y bar square? The variance of y bar is going to be that minus that. When I start plugging in all of that, I have that. Now, if I have that, okay, go to n plus 1 divided by n theta squared. Now, it follows that the y bar square is a bias estimator for theta square. If you take a look at this, because y bar square, if it's going to be unbiased, supposed to be expected value of y bar square equal to theta squared. But this is a bias because there's n plus 1 over n. Okay, and that was why to say it is biased. So we're going to say it followed that y bar square is a bias. However, that guy is an UMVUE of theta square because it's an unbiased estimator for theta square. Now, if you take a look at this, okay, what is the expectation? If you try to find the expectation of this guy, okay, it's going to be what? It's going to be n over n plus 1. What is the expectation of y bar square? This guy. You see that? So this guy, cancel this guy. What do you have left? Theta squared. Okay, so that is the reason. Okay, I think I put some problems here. Even I think my time is up. Okay, but if you're given this, how do you show that the maximum order is that? You remember the formula I gave you before for the maximum order, because you need to first figure that guy out. The moment you figure that guy out, then they can ask you to find the minimum variance unbiased estimator, okay, for theta. But before you can find minimum variance unbiased estimator, you're going to use this. You need to find what is the expected value of what? Of yn. Expected value of a random variable. So you're going to make use of this. You'll be able to show whether it is unbiased or not. I think I'm going to maybe I'm going to make 2-minute video to explain this, and I'm going to join that with this video, okay, before I post it on the YouTube. Any questions today on the this on what we've done? Any question? Is there any question? Go ahead. I think 20. When is 29? Did I put 29? I think 29 is today is what? 20 what? Oh, they're not to 29. Yeah. You're welcome. What question is that? Oh, and there's no way you can. No, you can leave that. At times could be technical, but there's no problem. But if you're able to answer all the question, I should be fine. Yeah. Okay. Yeah. a probability density function, okay, as this. And of course, they ask you to show that yn is a yn, which is a maximum order statistics, is sufficient for theta. Okay, at times we can actually have a situation whereby the maximum order statistic is going to be sufficient for theta, or the minimum order could be sufficient for theta, or the linear or the function of that could be a function for theta. Okay, so I'm going to show you how to figure that out now. Of course, if I want to show this, of course, I can go by way of Fisher-Neyman factorization theorem. Okay, so go by Neyman-Fisher factorization theorem. That means I actually need a likelihood. Okay, I need a likelihood of theta, okay, given y. Okay, now it's actually gonna have 3 raised to power n, then I'm gonna have a product, okay, yi or square, where I start from 1 to n, then I'm actually gonna have theta raised to power 3n. So this is gonna be the likelihood. Okay, so if this is a likelihood, of course, if you take a look at what I have right now, so if we make an attempt to arrange the observation, the sample observation in ascending order of magnitude, or in descending order of magnitude, of course, you can actually figure out the minimum that we can say, the maximum we can say, the y1 is going to be less than y2. Is going to, that will be after ordering that. Okay, so of course, this guy is actually going to be the maximum order. Okay, so if you want to go by way of factorization now, okay, we actually want to factorize this in a way, okay, that this is not going to be a function, you partition that, you split that into two, uh, in such a way that one is going to be a function of theta and the other one is not going to be a function of theta. Okay, if you take a look at this, I can actually rewrite this guy as having, indicating y, okay, y and theta, where that very I is going to be an indicator function. Okay, it's going to be an indicator function. Okay, now if you take a look at what we have now, we can actually say, okay, this can be partitioned into a situation where we got a function of theta, we don't have a function of theta, and it's actually, if you take a look at this now, and of course, it's going to be a product. Okay, now what this guy is trying to say is if you take a look at the product, the yi squared, of course, when the observation is actually arranged, in ascending order of magnitude, you'll be able to figure out the maximum. Okay, we can conclude here that the maximum, that could be the maximum order statistics could be sufficient as well, and at the same time, we can actually say the product of yi squared can also be sufficient statistic. Okay, so now if I go to the next question, another question actually asks, okay, show that yn has a probability density function, okay, of that. Don't forget, the yn is maximum order statistics. Okay, now we actually want to show, that the yn, okay, the f of yn, the probability distribution of maximum order is going to be that. Okay, of course, the other time, I actually told you, I gave you something like this, it's going to be n. Okay, the CDF, okay, raised to power n minus 1, the f of y. Okay, if you remember the formula of order statistic. Okay, so I'm gonna stop my share now, and I'm actually gonna use my whiteboard. Okay, so I'm gonna use my whiteboard. Okay, you're giving f of y given theta equal 3y squared divided by theta raised to power 3. And of course, 0 lie between y less or equal to theta. Okay. And of course, as you can see here, the maximum of y is theta. Okay, which is one of the reasons why we said the maximum order statistics is going to be the sufficient statistic. You can see here the state space of the random variable lie between 0 and the parameter theta itself. And that was why the other time, using the factorization theorem, we can naturally conclude arranging the sample size in the order of magnitude. I said in order of magnitude, of course, we can actually say that yn, the maximum order statistics, is actually the sufficient statistic. Okay, so I need to get the distribution. If I want to get the distribution of the largest, of course, we're going to make use of this guy, f of y given theta raised to power n minus 1, f of y given theta. Okay, now I need a CDF of this guy now. So the CDF of that guy now, okay, I need to integrate that. Okay, I'm actually gonna go from negative infinity. Okay, but when you take a look at the state space here is 0, so I'm actually gonna go from 0 to y. So I can decide to change this guy to t squared in that way, then I do the t. So in the hand, so when I actually do that, my f of y, I'm talking about the CDF now. Okay, the CDF now, which is an uppercase. Now it's actually, if you do your calculus problem very well, so it's going to be y raised to power 3 divided by theta raised to power 3. Okay, now if that is what you have, then all what I'm just going to do is to start plugging in. Okay, so when I start plugging in, okay, give me 1 second. Now, when I start plugging in now, okay, when I start plugging in now, okay, so I said the g of n of y equal n, okay, f of this, okay, raised to power n minus 1, okay, f of y, okay, so n, okay, I've gotten my f of y to be y raised to power 3 divided by this, everything raised to power n minus 1, and of course, don't forget the f of y is actually 3y squared divided by that. So when you simplify this guy, of course, at the end of the day, without wasting my time, I'm actually going to get 3n. Okay, I'm actually going to get 3n y raised to power 3n minus 1 divided by theta raised to power 3n. Now, when you take a look at this guy now, that is the distribution of the maximum order statistics. Okay, now since I got the distribution, I think I've already showed that now. Okay, so after showing that now, I think what it asks us to do again is to obtain the minimum variance or unbiased estimator. Okay, we want to obtain the minimum variance or unbiased estimator now. So what we actually need to do, okay, is to first obtain the expected value of yn, okay, using the distribution of the maximum order statistics that we've just derived. Okay, so I'm going to clean my board now. So we're going to want to figure out the expectation of that. Because don't forget, when I was explaining the Rao-Blackwell theorem the other time, the moment we figure out the sufficient statistic, either by using Fisher-Nehmer factorization theorem or by Skeffey, by Lemma-Skeffey, we can actually we can derive a situation, we can derive a situation where we can have access to minimal variance unbiased estimator by way of Rao-Blackwell theorem. So right now, I want to find the expected value of y, the maximum order. Okay, so don't forget, I'm going to use the state space from 0 to that, and y supposed to have y then f of this, which is actually now going to be I'm going to use a maximum order statistic distribution. So 0 to theta now. So y. Okay, so what I derived the other time, I'm actually going to plug that guy in 3 and y raised to power 3n, okay, divided by theta raised to power that, the y. Okay, now I want to integrate with respect to y. Okay, when you take a look at what I have right now, okay, so I can first like writing 3n divided by, bringing out the constant, and I have this guy, combining this guy with this guy. I'm actually going to have 3n, the y. Okay, so when you take a look at this guy now, okay, so I'm actually going to have 3n, that, then I'm going to have y raised to power 3n, okay, after integrating that, divided by 3n plus 1, then I shouldn't forget that's going to go from 0 to theta, okay? So what I'm trying to tell you now, we actually, wherever you see y, we're going to plug in theta, and we're going to plug in 0, we're going to subtract that, and in the end, I'm actually going to write what the expectation is actually going to be now. Okay, so the expectation of that guy now, we automatically get 3n, okay, or over that, then theta raised to power this plus 1, okay, divided by 3n plus 1. Okay, so all what we just need to do now is to simplify. Okay, we want to have an algebraic simplification of this guy now. Okay, so when you're trying to simplify that, okay, you're actually gonna get 3n divided by 3n plus 1 theta. Okay, so when you take a look at what I have right now, okay, we can now begin to talk about now. If this guy now is the expected value of yn, okay, now our estimator now is actually, so if this is expected, if expected value of yn is actually equal to what I have now, then I can, this is going to imply that I want to find the expected value, okay, of 3n plus 1 divided by 3n, okay, the yn, okay, take a look at this. This actually implies that, okay, 3n plus 1, for instance, if you're trying to make the yn the subject of the formula, okay, you're actually going to, this is what you're going to have when I take the expectation of this guy now, okay, when I take the expectation of this guy now, okay, the expectation of this guy now, of course, this is going to be 3n plus 1 over 3n expectation of this guy here, okay, and of course, this guy here is actually this guy. If I plug that in, you're going to see that this is going to cancel that, okay, and we're going to have theta, okay, which actually means, okay, the expectation of that is unbiased. Now, based on what I just did now, okay, I'm going to share my whiteboard again. So I'm going to tell the world, since the expectation of 3n plus 1 divided by 3n, the maximum order equal to theta, okay, so which shows that is a number. Yeah, so what I'm going to say now is I'm actually seeing this guy as my estimator, okay, I'm seeing that guy as my estimator, okay, so this is an unbiased now, it's an unbiased estimator, okay, for theta. Okay, now if that is an unbiased estimator for theta, if you take a look at this guy, this is a function of a sufficient statistic. Okay, this is a function of a sufficient statistic. Okay, now because the function of sufficient statistics, and of course we can actually say, okay, this is a function of sufficient statistics of yn, and therefore we can actually say the estimator, okay, is also a minimum variance unbiased estimator because of the fact that according to Rao-Blackwell theorem, okay, the function that we have here is more or less like the one I mentioned in class, which is a function of a sufficient statistic. Don't forget the sufficient statistic here is yn, and because this is a function of sufficient statistic, and when we take the expectation of this guy, it's going to give us theta, which means it's unbiased, okay, as indicated by Rao-Blackwell theorem. And when you take a look at this now, when you try to take the variance, go by what we did the other time, okay, you're actually going to see that this is going to have the minimum variance among the class of unbiased estimator, and because of that, we can actually conclude that the estimator here is minimal. It is minimal variance unbiased estimator. Okay, so this is where I'm going to stop in today's class. Okay, make sure you have a very good weekend. See you on Monday. Bye for now, everyone.